Section. Introduction. We're going to delve into the world of large language models, LLMs, and their application in solving mathematical problems. These models have shown impressive capabilities in reasoning and generating content, much like a human would. This has sparked a lot of interest in using them to tackle complex mathematical problems, especially those that require a high level of symbolic reasoning. Before the advent of LLMs, solving these problems was considered nearly impossible. It's a natural progression to use these models for mathematical problems that are presented in a text format. However, many of these problems require an understanding of geometric information. Even if a problem doesn't seem to be about geometry on the surface, using geometric methods can often lead to practical solutions. For example, this is the case in analytic number theory. With the introduction of models like GPT-4v, Gemini, and other multimodal large language models, MLLMs, researchers have started to explore how these models can be used to solve geometric reasoning problems. However, we've noticed that even the most advanced MLLMs still struggle with these problems. This is mainly due to difficulties in understanding geometric figures accurately. For example, GPT-4v often gives incorrect descriptions of geometric figures. It has trouble understanding the relationships between basic elements like points and lines, and it struggles to interpret things like the degree of an angle correctly. We think this might be because these MLLMs are usually trained with images and descriptions from a general domain. The skills needed to understand these are quite different from those needed for geometric reasoning. One way to address this issue is to improve current MLLMs by training them with data that includes high-quality descriptions of geometric information. However, this approach is challenging because the largest publicly available dataset of geometric problems is quite small, containing only a few thousand question-answer pairs. Also, current datasets don't include descriptions of geometric images and only cover a limited range of problem-solving methods. This limits the model's understanding of basic geometric elements and its problem-solving abilities. In this paper, we propose a solution to this problem. We suggest creating geometric visual text data using existing datasets and text-only LLMs, like ChatGPT. We use the unique characteristics of geometry to build a multimodal geometry dataset based on existing datasets. This process involves using the unique logic of geometry, its unique representations, its scalability, and other factors. We call our new dataset G-LLaVA. It contains about 60,000 geometric image caption pairs and more than 110,000 question-answer pairs. This dataset is 28 times larger than GeoQA+, significantly expanding the range of geometric problems it covers. Using G-LLaVA, we've developed G-LLaVA, an MLLM that can solve geometric problems much better than the current state-of-the-art MLLMs. Specifically, G-LLaVA 13b performs 27.4 better than LLaVA 13b on the GPS Minitus split of MathVista. Even G-LLaVA 7b outperforms the powerful GPT-4v on geometry problem-solving questions. In recent years, we've seen significant advancements in the development of LLMs. These advancements have greatly improved language understanding and generation, showing near-human proficiency in a variety of tasks. At the same time, the success of LLMs has inspired research into how they can interact with vision, leading to the development of MLLMs. These models have shown impressive abilities in creating detailed descriptions and engaging in dialogue based on visual inputs. However, even the best MLLMs struggle with geometric problems that involve diagrams and figures. Solving geometry problems is a challenging visual mathematical reasoning task. Early efforts focused on creating datasets manually. More recent approaches have introduced improved methods in datasets, aiming to enhance both performance and explainability. However, the scale of current datasets is limited, and traditional models haven't achieved the same level of performance in this area as they have in other areas of mathematical problem solving. Generating data using LLMs has been a popular area of research for some time. For example, some researchers have used pre-trained models like GPT-2 to generate training data for classification tasks. Others have improved the quality of generated datasets using a bi-level approach or used the influence function to select in-context examples to aid data generation. With the introduction of powerful LLMs like ChatGPT, automatic data generation has become more common. Many recent studies have used data generated by ChatGPT to perform instruction tuning. Section Summary. Large language models, LLMs, have shown great potential in mathematical problem solving, but they often struggle with comprehending geometric information. To address this, we propose a method to augment LLMs with a new dataset called G-170K, which contains geometric image caption pairs and question-answer pairs. With this dataset, we developed G-LLaVA, a multimodal large language model that outperforms existing models in solving geometric problems. Section: Observation. We've noticed that even the most advanced multimodal language models, MLLMs, while skilled at understanding everyday visual scenes, struggle with interpreting geometric figures. These figures, which are often simple for humans to comprehend, pose a significant challenge for these models. For instance, when we tested these models on geometric figures, the descriptions they generated were often inaccurate, a phenomenon we refer to as hallucination. Specifically, we found that models like GPT-4v had trouble understanding the relationships between basic geometric elements such as points and lines. They also struggled to accurately interpret these elements themselves. Smaller models like LLaVA 1.5 and Mini GPT-4 had even more difficulty identifying the types of geometric shapes in a figure. This inability to correctly interpret geometric diagrams could be a major reason why these models fail to solve geometric problems. However, real geometric diagrams usually have clear and well-defined relationships among their elements. We believe we can use this characteristic of geometry to create datasets that can help these models better understand geometric figures and reduce hallucination. While there have been attempts to tackle multimodal geometry problems in the past, the available geometry datasets are limited. The main issues with existing datasets are: they are small in size, they lack detailed descriptions for geometric images, and they don't offer a variety of problem-solving methods and answer pathways. These limitations make it difficult for MLLMs to accurately understand geometric elements and provide precise geometric solutions. To address this, we've used the characteristics of geometry to build a multimodal geometry dataset based on an existing dataset. This new dataset includes an alignment dataset to give MLLMs basic geometric knowledge, and an instruction tuning dataset to improve the model's ability to understand user instructions and generate accurate geometry solutions. Image caption datasets are crucial for training MLLMs to understand the context of images, which is key for aligning image and text modalities. However, in the field of geometry, there's a lack of datasets that provide detailed descriptions of geometric diagrams. To solve this problem, we've proposed generating image descriptions from labeled question-answer pairs. We used a text-only model, ChatGPT 3.5, to create image captions based on these human-labeled pairs. This method uses ChatGPT's strong understanding ability to produce descriptions for geometric diagrams. We've also generated question-answer pairs to help the model understand geometric diagrams, focusing mainly on their basic elements. We used ChatGPT to convert human-labeled logical forms into clear descriptions that cover various geometric elements and their relationships. After creating these diagram descriptions, the model began to produce contrastive question-answer pairs. These pairs are designed to examine different aspects of the diagrams, such as the presence of certain geometric elements or the accuracy of the relationships described. This method allows the model to understand geometric concepts and accurately analyze and interpret the details in geometric diagrams. After aligning the model with the constructed alignment data, the model was better able to interpret the geometric diagram. However, it still struggled with solving geometric problems. To address this, we built an instruction tuning dataset based on existing datasets with the help of powerful language models. We designed strategies to expand the question-answer pairs in existing datasets, resulting in a dataset containing over 110,000 question-answer pairs, the largest public geometric question-answer dataset available. We also introduced equation solving and value scaling strategies. In equation solving, we replaced specific values in the original question-answer pairs with unknown variables and prompted the model to construct the solution by solving the equation. This helps the model generalize its understanding of the problem and apply similar reasoning and solution steps to different scenarios. In value scaling, we augmented the data by scaling the length values in the question-answer pairs. This makes the model more flexible in handling different numerical inputs and helps refine the model's computational and reasoning capabilities, thereby contributing to its generalizability. Section summary. Most state-of-the-art language models have difficulty comprehending geometric figures, resulting in severe hallucination and inaccurate descriptions. To address this, a multimodal geometry dataset is constructed, consisting of an alignment dataset for fundamental geometric knowledge and an instruction tuning dataset to improve the model's ability to understand user instructions and generate accurate solutions. Additionally, image descriptions for geometric diagrams are generated using labeled question-answer pairs, and contrastive question-answer pairs are created to facilitate the comprehension of geometric concepts. Finally, an instruction tuning dataset is constructed by expanding existing question-answer pairs using strategies such as equation solving and value scaling to improve the model's generalizability and problem-solving capabilities. Section: Reformulating Condition as Unknown, RCU. We've developed a new approach to creating multimodal question-answer pairs, inspired by previous research. Instead of asking questions in the traditional way, we flip them around. We ask for the values that were originally in the condition, and only keep the data that has the correct answer. This method repeatedly exposes our language learning model, LLM, to the relationships between variables, equations, and their solutions. This repeated exposure helps the model understand the connections between different elements in a mathematical problem. We also rephrase both the questions and answers. This exposes the LLM to a wider variety of language and phrasing, making it more robust in understanding and generating diverse sentence structures. As a result, it can handle similar questions phrased differently and provide accurate answers. Our model uses the G-LLaVA architecture. It's primarily made up of a large language model, LLM, like Llama 2, a pre-trained vision transformer, VIT, as an image encoder, and a projection layer. The projection layer maps the visual features from the image encoder to the same dimension as the LLM. During the inference process, the image encoder extracts visual tokens from an image. These tokens are then mapped to the dimension of the LLM's embedding space via the projection layer. The mapped image features are combined with text embeddings to serve as the input to the LLM. The LLM then starts generating the next token. We train our model, G-LLaVA, in two phases: geometric visual language alignment and geometric instruction tuning. In both phases, we use the conventional language modeling loss. This can be explained as follows. F represents the model, I represents the geometric figure, S_tar and S_in represent the target and input sentences respectively. S_t_tar denotes the TTH token of target output, and L stands for length. We generate alignment data and instruction data using the training set of GOQA+ and Geometry 3K. The contrastive question-answer pairs in the alignment data are generated using Geometry 3K, which features human-labeled logical forms. GOQA+ covers the training set of GOQA and shares the same validation test set as GOQA. Our approach results in 60,000 alignment data samples and over 110,000 instruction data samples. We compare our model with other multimodal large language models, MLLMs, on geometry problems on the MathVista Minitus split. We also compare our model with traditional in-domain models on the test split of GOQA. For implementation, we use ChatGPT for data generation and LLaVA as our backbone. We use Llama 2 as the language model and the visual encoder of a pre-trained vision transformer, VIT. The input image resolution is 336 by 336. We conduct experiments with both 7B and 13B LLMs. During the cross-modal alignment process, only the projection linear layer is trainable. During the instruction tuning phase, both the projection linear layer and the language model are trainable. The learning rate is set to 3 × 10⁻⁻⁵. For evaluation, we use accuracy as the metric. Some previous studies report results using top 10 accuracy, but our experimental results directly report top 1 accuracy. During instruction tuning, we enable the model to output the choice in a fixed format. For evaluation, we directly use regular expression to extract the predicted choices from the generated answers. If the regular expression fails to extract a valid answer, the answer is considered false. Section Summary. The Reformulating Condition as Unknown, RCU, approach involves designing new multimodal question-answer pairs that ask questions in reverse, focusing on the values originally present in the condition. Paraphrasing is also conducted to expose the model to a broader range of phrasing and language variations, making it more robust in understanding and generating diverse sentence structures. The model architecture consists of a large language model, LLM, a pre-trained vision transformer, VIT, as image encoder, and a projection layer to map visual features to the LLM's embedding space. The model is trained in 2 phases, leveraging language modeling loss. The dataset used for training is generated from GeoQA+ and Geometry 3K, resulting in alignment data and instruction data. The model is evaluated using accuracy as the metric, with top 1 accuracy being reported. Section: Main Experiment. In our main experiment, we put our model, G-LLaVA, to the test against other multimodal language models, MLLMs, using a subset of the MathVista benchmark. The results, as shown in the table, indicate that our approach of using geometric cross-modal alignment and instructing tuning on our dataset significantly enhances the geometric problem-solving capabilities of MLLMs. In fact, our specialized model, G-LLaVA7B, even outperforms the robust GPT-4V in solving geometric problems. We didn't stop there. We also compared our method with the current best techniques in the field of geometry problem solving. The table illustrates that our method significantly improves the top 1 accuracy, a measure of the model's ability to correctly predict the first choice, over the existing top techniques. What's more, our model's top 1 accuracy even surpasses the top 10 accuracy of the baseline models, indicating a substantial enhancement in predictive precision. We also wanted to see how G-LLaVA performs against baseline models on problems of varying difficulty levels. Here, difficulty is measured by the number of operations or reasoning steps required to solve the problem. As the table shows, our G-LLaVA consistently outperforms the baseline models by a significant margin across all difficulty levels. We further tested G-LLaVA against the baseline models on different types of geometric problems, such as those involving angles, lengths, and areas. The results, as shown in the table, suggest that G-LLaVA consistently outperforms the baseline models in these various geometric problem types. Finally, we evaluated the effectiveness of the cross-modal geometric alignment phase. We compared the performance of the model with and without this alignment phase. The results, as shown in the table, suggest that this alignment phase significantly enhances the model's ability to interpret images, as also demonstrated by the qualitative result in the figure.